Good morning, and welcome to the Wednesday morning Invited Talks session. Our first speaker is Orsola DeMarco, an astronomer who works on aging intermediate mass stellar binaries using observations and 3D hydrodynamic computations. She received her PhD in 1997 from University College London on spectroscopic studies of hydrogen-deficient stars, after which she had research fellowships at the Polytechnic of Zurich, University College London, and the American Museum of Natural History in New York. She became an associate professor at Macquarie University in Sydney, Australia in 2009, and a full professor in 2015. In 2013, she was awarded an Australian Research Council Future Fellowship. Here to talk about stellar collisions at the limits of HPC is Orsola DeMarco.
Hello, everybody. My computer is now dead. No, it's not. It's good. Okay. So, of course, in the good tradition of astronomy talks, the first thing I'm going to do is change the title of my talk, and that's because I realize that as perhaps one of the very few astronomers in this conference, I really should be a little bit more inclusive and not just talk about my simulations, but tell you a little bit about what HPC can do for astronomy as a whole. So let's talk about astrophysics at the limit of HPC. And so let's go. The reason I start with this wonderful trailer from Fortnite is first and foremost because when I told my daughter, my 15-year-old daughter, that I was starting my boring talk with Fortnite, her jaw dropped and she didn't speak for 6 whole seconds, and it was so satisfying. The second reason, if you have a teen, you know what I mean, right? The second reason is that there's a lot of HPC programming that goes into computer games. It probably is one of the drivers of the industry. And there's a lot of similarity with astro simulations. Of course, visualization is the real key part in computer simulations, but physics needs to be programmed in because otherwise it won't look real and the player won't be very satisfied. So things like inertia, the way bodies move in response to air and water, gravity, of course, that has to be in there, and of course light, mostly because the viewer needs to recognize the scene through shades and shadows and reflections. Many of those laws of physics, much of that physics has to go into astro simulations. So an astro simulation is nothing but basically we want to understand all them clouds out in space. What do? Where do they come from? So we simulate them in time by putting as much physics as we can stuff in the computer and then running forward in time the simulation. Those rules of physics are much the same. We have, of course, inertia and aerodynamics. We call that hydro. And then we have the laws of gravity, of course, gravity rules in astro, and light. Light not so much because of how we see things, but because light can push and exert forces on gas. Now, visualization is important in astrophysics, but only because we want to study our outputs, our simulation outputs. Not so much while you're simulating. You don't really care what's happening in the box while you're doing the simulation. Now, the rules of physics we may need in our simulations are a few more than the ones I just listed. You might have to have thermodynamics, actually have to have thermodynamics. Magnetic fields may be important because they exert forces. Chemistry can be important. Chemistry in astronomy is everything that has 2 atoms. We call it chemistry. Dust may be very important. I'll talk about planet formation shortly, where dust is absolutely fundamental. And then you may have things like neutrino physics, and you may have to do the whole shebang in special and general relativity framework if you have very strong gravitational fields like near black holes, or when you have supersonic and sort of jets going close to the speed of light. Now, how do you stuff all the physics into the computer to then press go and get the simulation? Well, you start with Newton's second law. The force imparts an acceleration to a mass. Now, that is too simple to put in the computer. It's just not going to do much for you. You need to really break it out. So the forces that we are contending with are, of course, gas pressure. You may have magnetic forces, gravity, always, and things which are really pesky, like viscosity, that are hard to really describe. After the physicists, you have to have the help of the mathematicians to formalize all those forces and express them as a function of the fundamental quantities, such as magnetic field strength B. So the equations, very quickly, as you can see, get quite messy. Now, you don't have just that equation. That's basically F equals ma, also known as Euler's equation in a hydro. You need a few more equations to close your system. So you get like 5 or 6. And the more physics you put in, the more equations you have. Now, that cannot be solved analytically with your Mathematica or even with your pen and paper. You have to discretize it in order to solve it numerically. Now, the discretization, at some point I had 6 slides of discretization, and I thought, no. So it comes down to taking all those integrals into summation and all those differentials into difference equations. And here I hide tons and tons and tons of work and methodologies designed by mathematicians and computer scientists together in order to make these numerical solutions be accurate and also work fast. So every one of these methods has a computational cost and an error budget. And of course, when you discretize, you're discretizing onto a grid, which is you taking your cloud, your space, and splitting it into small segments. Whenever you discretize anything, you're going to lose resolution, of course. And of course, the discretization is also in time, because as you evolve your cloud further in time, you have to do so in discrete time steps. And that, of course, carries another error budget. So you can see very quickly you can have a big problem of accumulation of error. Now, why do we carry out simulation in astrophysics? Where do they fit in our thinking loop? This is a good old schematic of the scientific method. Of course, we see things in the sky. We have a lot of nice questions. That blows up. Is that common? Is that uncommon? There's a lot of galaxies. What shapes do they have? However, in order to go from these questions to formulating hypotheses that make quantitative predictions that then can be further tested with more observations, you need to do a little bit better than the little questions that you may have, like looking at the night sky or even looking at a beautiful Hubble Space Telescope picture. You need to make a model that, by chucking all the physics in, gives you some outputs, which are numerical outputs. And those outputs will say, well, I think I should be observing another 10 of these objects in the next century. Or I should see more clumps, or I should see different shapes. So let me tell you a little bit about modeling in astrophysics, and I picked 3 of the many problems we work on at 3 different scales. On your left, you have a little baby planet being formed in a little baby disk near a little baby star. This size is the size of the solar system, about 100 astronomical units, where the astronomical unit is the distance between us and the sun. At the other end of the scale, you have the whole lot, the universe. The universe, 13.7 billion years old, so that's the time scale you're modeling. And of course, you have a size scale that's the same thing in light years, because the wonderful thing of astronomy is that we have a time machine. When you look back at something that's very far, you're also looking back at something that's very early in time, a long time ago. In the middle scale is what I do, stellar collisions. This is a nebula coming from a colliding star or an interacting binary. They're biggish, but they're not that big. They're not too much bigger than our solar system. So let's start with the planet formation. So what are the questions that you, I, the people in the street ask about planets? The one that I bet you can ask anybody in the street, and they will have thought at some point about it. Are we alone? Are there other planets that are habitable by life forms that somehow we would recognize as life? The next question, going into the sort of the Matryoshka doll, is if there is life, we need to understand how water arises in planets, how organics are moved around or arise in planets. We don't have an answer to that. Now, if we have planets, then we really need to understand how do they form from the disks around nascent stars. And of course, how many form? When? Do they move around? Is our solar system a typical byproduct of planet formation? Now, we've been lucky in planet studies that we've been deluged with data in the last 10 years. 1991 was the first planet discovered and 51 Peg, And today, thanks to instruments like the Kepler Space Telescope that measure planetary transits, we have thousands of planets. And this beautiful picture from Kepler called the planetary orrery puts them to scale. This is not all of the ones we know, it's just many of the ones known at the time. Now, another great advance in planet formation has been the discovery of the baby planets, planets forming in the disks around nascent stars. Now, ALMA has been fundamental for that. That's the newest and best radio telescope. And it has found a lot of these forming systems which are amazingly diverse. You see here the gaps. And the gaps, of course, have told astronomers right away that perhaps they're carved by planets. Now, this tends to be true, but not always. There's other ways of making gaps. So how do we use the gaps to understand the formation that is going on in this planet? Simulations is the way we go. Now, the type of physics that you need in order to do simulations for planet formation is kind of the whole list. You can avoid all this high density, high gravity stuff, but you really have to include the chemistry and the dust. And that is really tricky, particularly the dust when you have two fluid hydrodynamics is really messy. There's a lot of numerical problems. Now, I had 3 or 4 examples. There's so much activity in this field. And the interesting thing is when you talk to colleagues who do planet formation simulations, you realize that they don't agree at all. They actually, when I said I wanted to show these beautiful simulations of forming gaps, I had at least 3 colleagues and friends of many years saying, they're wrong. And of course, when I asked them, this is a group in Melbourne, the same question about my colleagues, said, no, definitely not. So it's a very interesting, very active field. The reason for all the discrepancies is that there isn't really an agreed right simulation. Now, this simulation, you have a bunch of planets put in disks, and they form gaps. And the gaps are compared to the observations from ALMA. Now, interestingly, how do you know simulations are right? This is true of all simulations. Well, first, you need to verify your codes. And how do you do that? I mean, a code can be tested against analytical predictions. That's fine. A code can be compared to another code. But of course, both codes could be wrong. The other thing you do is you validate your code. And that's, of course, done with observations. And in this case, the validation was that the gaps are pretty good compared to observations. But you see those little wakes that come from the planets. Those are never observed. So the question is this telling you something is really wrong about the simulation? Or is it telling you something, maybe just a detail is wrong? So we're really in the midst of even just figuring out whether these simulations are right at all. Now, this type of simulations take about a couple of weeks on a relatively few cores, and I'll come to the problem of gravity and parallelization later. Now, at the other end of the scale, we have these cosmological simulations. The first one came out in 2005, and the idea of cosmological simulations is to understand how you go from the very early days that are depicted here on the left by the cosmic microwave background. This is the light that started 300,000 years after the beginning of the universe. And as soon as the universe became transparent, the light starts streaming. And we see it today as this background, very low frequency, very low energy background. What matters in this background is not so much the background itself, is the fact that it's blotchy. It was a huge discovery that gave people Nobel Prizes. And the reason it's a huge discovery is because before we discovered them, we couldn't understand how from a smooth background, you got a very clumpy structure of the universe today depicted on the right. What we need to understand is how we go from the cosmic microwave background blotches to today's incredible structure seen here in a Hubble Space Telescope deep field image of a little tile of the sky. So many galaxies with different masses, different shapes. In each of these galaxies, there is a black hole, a supermassive black hole of a different mass. So how do you bridge this gap between the then and the now? Now, simulations have done that job. And today, I'm going to tell you a little bit about this particular very modern cosmological simulation that takes the mass in a co-moving volume at the time pretty much near the Big Bang and evolves it through time as the universe expands and looks at all the clumping and filamentation of the dark matter substratum within which you get the formation of clusters of galaxies within which black holes form, merge, and grow. And you look at all this growth, and then you have to figure out, is this even remotely correct? Now, before I tell you a little bit about the results of this, I want to tell you about the simulation itself. This was carried out with Blue Water. It's a computer at NCSA. It is not listed in the top 500 because they didn't want to, but probably will figure pretty highly there. It is an amazing simulation that used 36 million CPU hours and used 300,000 cores. Now, when I read this, I thought I said some zeros wrong. This is pretty much the whole machine. This is an incredible simulation that scales particularly well, and the reason it's so good is that Gadget 3, Gadget is a very common SPH code in astrophysics, but it was absolutely fine-tuned to the architecture of the machine and to the nature of the problem. And only so can this scale so well. The other reason it scales very well is that what you do in cosmology, you take these big parts of the universe, and the reason you want a lot of it is that you want things to happen in it that then you can count and look at frequencies of, for example, masses of the black holes, masses of the halo, or the dark matter halos in galaxies. So here is just the one result I selected out of the many results that came from blue tides. And on the left, you have the blue tide simulation that goes from the beginning of time until 0.6 billion years after the Big Bang. You can't really do much more. As you saw, it was already a very long simulation. After that, what you can do, you can analyze the simulation, but in order to validate, in order to understand whether anything was right in the first place, you really need to bring that simulation a little bit further in time so that we can observe some things. And the way they do is they take the physics down, they strip a lot of the physics, and they concentrate on specific aspects. So the right panel is blue tides taken forward in time to the modern day, and only looking at dark matter halos. These are halos of matter. You know dark matter is funny, it behaves gravitationally, but we don't really know what it is. But it does form around clusters of galaxies, and this is measured through the gravitational interaction and the galactic light. And so we can actually compare with observation, and this is a wonderful validation that blue tides was at least partly on the right track. Now, I move on to stellar collision, which is what I work on. And I wanted to give you a little motivation about what are these stellar collisions. Collisions are a little bit of a gimmick term. We actually call them stellar interactions. What you're seeing here is a merging of two intermediate mass stars, 5 solar masses or so. It was the brightest star in the galaxy in 2002 for about 5 minutes, and it illuminated interstellar dust, giving you this impression of an expanding cloud. It's actually not expanding, it's just stuff that was there that got illuminated by the pulse of light. So on the left, you have the same object caught at a particular moment in time. It's beautiful. It was on the front page of the New York Times Science page on a Tuesday. And mostly we don't see that because you don't get lucky with all that dust around it. Mostly we see what's on the right. On the right, we plot the light of your interacting star versus time. We call it a light curve. And as you can see, there's a lot of features here. There's some slow rise, some up and down, and there's a huge outburst, and it comes down. There's a dip before the outburst. And it is that light that we try to mimic and model with the simulations in order to understand whether we understand what's going on in the inside. Now, stellar collisions are really varied. What you saw before were middle stars, kind of boring, like the sun, just a little bit more massive. Here we have a type 1a supernova remnant. This is white dwarf merging with one another, if we got that scenario right, leaving behind this nebula. This is actually the ejecta from the merger of the two white dwarfs. The star in the middle is disintegrated, but the stuff around with all the newly formed elements is left behind. This was a Kepler supernova of 1604 that was actually a naked eye object at the time. Here we have another 3 very diverse nebulae coming from very different types of phenomena. On the left, a very massive star that went off in 1841 is actually seen with not quite modern telescopes, but almost modern. And it left behind this nebula that formed right there and then. The star was naked eye, again, was very, very bright. We don't know what type of interaction gave rise to that. We know there is a very eccentric companion around the star that erupted and probably could have triggered those eruptions. There's a huge community working just on that object with simulations and fighting, like the planetary community fight. Astronomers fight a lot. And then on the right, you have 2 middle-sized nebulae. In this, we didn't witness anything. We don't know what happened because we were not there. The explosion probably happened about 1,000 years ago, but it left behind something that should tell us, right? There's a lot of detail here. How do I know what happened in the stellar collision in the middle, even if I haven't witnessed it when I look at the nebula? Of course, I would not be able to walk out of this podium having talked about stellar collisions if I didn't say anything about gravitational waves. We all know we have 11 events now. LIGO, this is the Lago Louisiana. There's a similar one in Washington State and one in Italy. And the 3 of them together confirm each other's detections and, of course, triangulate in the sky to find the approximate place where the thing went on. And the reason we want to know is because we want to follow it up with regular telescopes to see if there is an electromagnetic counterpart to that gravitational wave. Now, we know these gravitational waves so strong that we can detect them. come from merging black holes. Most of the events have been black holes. One event has been merging neutron stars. The merging neutron stars are very interesting because we did find an afterglow, and through the light, we could study tons of things. Through spectroscopy, we could find the first confirmation, I get goosebumps every time, that gold is indeed made in merging neutron stars as nucleosynthesis theory predicts. So what do we want to know about these collisions? By now you know that they're very varied, right? There's just so many things that merge and do things like that. We just want to know, the first and most important question is when you have an interaction between two stars, no matter what stars, do you leave this interaction with a binary that has not merged, or do you have one star because it has merged? The reason why this is so important is that those gravitational wave mergers that you saw in the previous slide come from a series of interactions, all of which would have been outbursting and giving you those light curves. After these many interactions, you get this nice binary neutron star that goes on and merges, and then you get the gravitational waves. So people who study this phenomena really need to understand what happened before, and that's where simulations can help. We want to understand how the nebulae that you've seen in the pictures relate to the explosion in the middle. We want to understand what the light that our simulations predict, whether that light matches the observation. That is the way we validate the simulations. And then we have all kinds of funny blue sky questions like, what happens to planets? Planets are like companions to stars. The star expands. Do you eat them up? Oh, yes, you do. Do they survive? Oh, no, they don't. So there's lots of little questions like that that are ancillary, but still very interesting and important. Now, instead of explaining to you how these interactions work, I decided to show you one of my students' movies. This was a movie that was rendered for a general audience. It was captioned, so if you look at the caption, it'll tell you what's going on. It was, it's not maybe the most scientific, but it's really pretty. And Thomas told me, you show it to anybody you want, but you have to take responsibility for the music, okay? And that is because it's a bit cheesy. I myself think it's lovely, so just sit back and enjoy. Read the captions because they matter in the story. You can sing along if you want.
Giving me all you got. Your love has captured me. Over and over again, I try to tell myself that we could never be more than friends, and all the while inside sweeter love grows, and heaven's there for those who fool the tricks of time. With the hearts of love, they find true love in a special way. The closer I get to you, the more you
Apologies for the slightly abrupt ending, goes on to some observations that you've already seen in the slides. I should point out that Thomas submitted this for a competition of the Australasian Fluid Dynamics Society and actually won it. So there you go. The music, I think, did it. Now, before I tell you more about the simulation, this is a big production run, and I'll tell you some interesting things in a second. I want to tell you what are the results, things that you can get from this and similar simulations. And there's quite a lot, and some are a little bit boring, to be honest with you, and very technical, and it's not really worth, but there are a few that are actually quite inspirational. On the left here, you have an artist's rendition. In the background, you have a binary. That binary survived the simulation type interaction that you've seen. In the front, you have 2 planets that were discovered around this binary. The question was, my God, that binary went through a common envelope. All that goop, you see the cotton candy that you saw in the simulation at the end, must have engulfed the planets. How did they possibly survive that? The answer, through simulations, is that they don't. On the right, you have the in-spiral of a planet through the goop that you've seen in the simulation. It goes in pretty fast. The 2 lines are 2 different resolution tests, but ultimately they don't survive. So the only conclusion of this is planets like that, if the observations are indeed correct, remember, observations are not always correct, is that they're second generation. They formed from the goop. Now, this is quite interesting. It's a completely different methodology of planet formation that hopefully will be investigated in the future. Another thing we found is when your planet dies in the envelope, actually spins up that envelope, and that can explain fast-spinning giant stars. So that's another cool result. Another one is kind of a bit of a byproduct of the simulation. On the left, you have density cuts in the equatorial and perpendicular planes of the simulation you've seen the movie for. At the bottom right, you see how that wonderful picture, this is in the vertical cut, you have this very interesting symmetric butterfly-like thing. And the question is, can you make nebulae that look like the ones on the right, all of which are known to come from these common envelope interactions, by doing with something like in the simulation? So this is another way to validate. So recently, I have given my outputs, these are smooth particle hydrodynamic output from our simulations, and I've given it to colleagues who use instead adaptive mesh refinement grid codes. And the reason is that we know that the star in the middle of end of my simulation emits a very fast and tenuous wind that propagates through this mold that you see on the left and shapes the mold, shapes itself, and should result in a nebula with a given shape. In the middle, you have the simulation of the fast wind having plowed through the mold left behind by the binary interaction simulation. And as you can see, you have this counterplot of the jets that come out of it. 2 main results came out of this. Actually, the paper, this simulation, the better of these simulations has finished this morning, so it's very, very fresh. And Amy Zhu is about to submit the paper. What is interesting is you see how collimated the jets are. Usually in astrophysics, when we see collimated structure, we are sure there are magnetic fields. In this case, there are no magnetic fields, so we can show that collimation is not just a byproduct of magnetic collimation. It can happen in hydrodynamics as well. The other interesting thing is you see how the lobes are very different in size, and they're very similar in a sense to that picture on the right, where for a long time people have seen the Kabalash Nebula, and we wonder why the lobes are so lopsided. And ultimately we can show this is the byproduct of the inherently 3-dimensional nature of this interaction. So the funnels in the middle are they look very similar, but they're just ever so slightly different. And the density contrast is so enormous that it just drives enough difference in the 2 lobes. Let me tell you a couple of things about the simulation. The first thing is, what is the physics that we have in these simulations? On the left, you see I haven't ticked many things. It's very little. We would absolutely love to have magnetic fields to understand better how dust in the expanding envelope plays a role. We can't at the moment because on the right, you can see very clearly the problem. The wall clock times of the simulations is huge. I put 6 months. It's actually more than that. It's really at the limit of our patience and also the limit of reliability of running the simulations for very long. The reason they took so long is that they don't scale very well. So we're really talking about 100 to 200 cores, and then you absolutely plateau. You don't gain anything. The reason for this bad scalability is, maybe I do this? Oh, really? I'll be there with you. Okay. The reason for this bad scalability is gravity. When you have to calculate the gravitational attraction of everything with everything, you need to solve this equation, which is the Poisson equation, at every time step. Basically, the density distribution, your star, dictates the potential, the gravitational potential, which you need to understand the gravitational forces. Solving that is really tricky. You could do it by direct summation of all gas to all gas, but that would take forever. So there are tricks like building these trees where you split your domain into blocks, and the blocks are very small where there is a lot of mass, and then you can consider a faraway block as one block instead of doing direct summation of all the particles in it. However, no matter what you do, it's slow. Now, part of this is the reason why many more groups have joined this effort, particularly now. As you can see, the dates here are 2016, 17, 18. And the reason is we need to understand how this common envelope works properly. Otherwise, we are at a roadblock in order to understand the gravitational wave emitters down the line. We absolutely need to figure this out properly. And to figure this out properly, you need more people. So these are all the groups in the world that are at the moment verifying codes by comparing them and looking at what you can add without having too long a wall clock time. Now, this is my last slide, and I would like to talk about this collaboration that I'm carrying out with Louisiana State University, the Center for Computational Technologies. And what they are doing, they have built a code called OctoTiger that instead of using the usual MPI parallelization scheme, uses HPX. The key of HPX is that it's C++ compatible, so it's actually C++ standard, and it can program a computer to use its GPUs and CPUs at the same time. What is amazing about this, on the left you have a merger of two main sequence stars published earlier last year, and what you can see in the middle is that this code scales pretty well this particular simulation to 4,000 cores. This is unheard of in my business. And so the hope is that we can scale the simulation so much better that we are going to be able to add a lot more physics and just dispatch all the physics and all the calculations to processors in the most efficient possible way. On the right-hand side there, you have a scaling test, which in my business, the scaling tests always are like curves that go like this, right? So they plateau very quickly. Here, you show that as you increase the resolution and you increase the number of processors that work on it, you're just actually increasing the speed of the simulation. There is a paper on OctoTiger HPX at this conference tomorrow at 11:30 in room 401, and all the technical details will be there. So I just wanted to conclude, and given that I told you a little bit about how we collaborate with mathematicians, physicists, and computer scientists, it is this type of collaboration that I think are the future of astrophysics. Not just HPC in astrophysics, but astrophysics, because if we don't understand our observations, we're dead in the water. Now, I depicted this as the three, Newton, Gauss, and I used, help me here. Turing, oh my God, I had a senior moment here. But in fact, it's this collaboration that is important. It is the collaboration between all the people in all the companies and in all the universities working on hard computational problems and kind of helping the astronomers to make their codes run better, faster, with higher resolution. There are a few astronomers who actually bridge this, the ones who usually build the really successful codes, but not that many. There are more astronomers like me. I'm much more of a physicist than I'm a computer scientist, who use the codes and have ideas in physics and really need the help of the computer scientists, such as the collaboration we have with CCT in Louisiana, to really get these codes better and to use the machines properly. I don't even know what machine I'm using. Just put in the code and then I'm closing my eyes. What we really need is to make sure the architecture are compatible with our codes and with our physical problems. So with that, I'm thanking you. I have a little picture of myself drawn by Sasha Matthews. She's a cartoonist. She was doing this for charity, so I paid $20, the best $20 I've ever paid in my life. And she made myself superhero. And as you can see, she looked at my website and found that I really like binary interactions, and she put binary interactions on my shirt. And so with that, I stop. Yeah.
Thank you, Ursula. And we do have time for a few questions. If we have some questions, I'll ask if you can please go to the microphones that's in between the aisles. Let's see. Okay. And I'll start with a question, and that is, you talked about the collisions with stars between two. Do you have it also where after they've collided, they can collide also with others, and what occurs during that collision as well? Once you've gone through one collision, and then I think the second.
Absolutely. And in fact, there's two examples of this. The first one is in 2012, we discovered that stars, particularly massive stars, are really interesting, the ones for which we see gravitational waves. They interact, they usually are born not just in pairs, they're born in multiplets, in quintuplets, sextuplets. And of course, these interactions can happen at different phases of the lives with different numbers of companions. Now, doing two is already pretty difficult, so doing more is quite difficult. But one thing I have tried before is collisions with two or more planets. Okay. One idea was that if a planet hits a star, maybe it dies off, but it also expands and spins up the star. May this save the next planet colliding, so one planet sacrificing itself for the other. And it turns out that, I don't know yet, but ultimately, it's possible. So multiple collisions can do additional things and multiply the number of effects we might be able to explain in the observations.
Thank you. We have a question at microphone 4.
Yeah, I have a question. You talked about a binary and then the tidal dissipation making this binary collide, and then it can survive as another stable binary. Don't you have tidal dissipation there as well? Why is it sometimes stable and sometimes not?
That's right. So in the last simulation, that was two similar stars like the sun, and those definitely, they will tidally dissipate and destroy themselves before they even won, right? But in the simulations that I do, it's a little bit different. You have a really big giant. The giant has a core that's like a pea inside. It's an enormous structure. The envelope is fluffy, very, very fluffy. The companion tends to be a pretty hardy white dwarf, really kind of solid, or even a main sequence star, which compared to the fluffy thing, it's a lot more dense. In that case, you don't tidally disrupt them, and what you do is the little companion siphons some of the fluff towards it, then it grows, then it goes in, but it's actually itself, retains its identity all the way to the core. Now, sometimes it doesn't get to the core. If it did, it would be tidally disrupted, just like you saw in the last simulation. But if you don't get there, because somehow you dissipate the envelope before you get close enough, then you have your surviving binary. And this is the type of binary we are looking to produce in order to form all the gravitational wave emitters.
Okay, thank you.
Thank you. And do we have a question? Okay. And I have one more question, too. And that has to do, I think, when we saw the video with the two, with the collision, it was over, I think, about 15 years. So if you could talk about the time frame with respect to the collisions, and especially collisions between two stars and collisions in terms of a planet and a star.
Absolutely. So the time scale of particularly the final part of the collision is dynamical, and the dynamical scale depends on what type of stars we're talking about. If you're looking at white dwarf, we're talking about minutes. If you're looking at fluffy stars like mine, we're talking about a year. And previous to that, the tidal disruption, the approach, the mass transfer, that also happens on relatively fast timescale. This simulations may not be looking at the time correctly for the early part. Well, that could be over maybe centuries, and then down to something that spirals very rapidly over a dynamical time of minutes to years. So they're very, very short. And it's funny that these simulations take about a year to in the computer. It's like real time. It's really fun in astronomy. And so, yes, so the times are very brief. With planets, depends what star they're going in. Sometimes planets get eaten up by main sequence star. We know from having found so many hot Jupiters, which are Jupiter-class planets very close to their mother star, that many others will have died into the star. When they go into a main sequence star like that, into a sun, we're talking about, again, they're in and destroyed in very short times, like days. But if you have a fluffy thing, so the planet's further out and the star has time to expand and become a giant, then the in-spiral could be centuries, decades to centuries, so still pretty brief. Now, we were interested to see whether we could observe it, and the star does react to it. It just gets fluffier and even bigger, and it rotates, but we might not have the time scales correct for the observations to actually catch it in the act, but we do see the aftermath in the form of these fast-spinning giants that have an extra enrichment of certain elements that must have been brought in by the planets that collided with it.
Okay. Thank you.
Thank you.
Okay. And we have time for one more question. Microphone 4, and we'll take the question at 5 as well.
You were first.
Okay.
So you were talking a lot about just binary star systems, but what if you if there was three, so like a three-body problem, what would the simulations look like then?
So, absolutely. So we haven't carried out trinary simulations just because it's so tricky to do even with two. Not tricky in like, it's quite easy to imagine, right? But it is definitely tricky for the computer. It just takes so much time. Every time you have close interactions between mass and mass, it takes forever. It grinds to a halt. However, you'd expect if the system, the trinary system was stable to start, then usually one star is very close and one is further out. So at the very least, this interaction might happen in two stages. So you have first what you've seen in the simulation, and then whatever you got left, whether you have a merger or a binary, might end up interacting with the third star. It's interesting, there's actually a paper right now that just came out. It's a partial simulation of a binary going into the envelope of a bigger star. So this is a bit different, right? It's a little compact neutron star white dwarf binary going inside as a binary, right? So you can imagine that's a pretty unstable thing, particularly once you add all the gas. And I would say the simulations at the moment are very much like toy models. They are for us to be inspired and think of new questions and new way to simulate rather than giving us direct results. So the answer is we don't really know how that proceeds.
Thank you. And we have time for
It's just a quick question. We know that type 1a supernovas are a standard candle for cosmology. Could you comment on what range our simulations will be able to bracket their brightness?
So that's just, you're putting the finger in a very big wound of astrophysics, right? So the fact that the type 1a supernova are standard candles, and we used to say, but we don't understand how they arise, and we don't even understand if they're standard candles. To a great extent today, this is a moot question because there's so many other methods that all give us the same answer. But what is still interesting is we don't understand supernova type 1a very well. We don't understand what makes them. We think it's either merger of two white dwarf or maybe just one big star giving mass to a white dwarf, and then the white dwarf is tipped over the Chandrasekhar limit and collapses. But the interesting thing of this, of our simulations and the way they partake in understanding what is going on with the type 1a's is that we want to understand, my simulation gives you a binary at the end or a merger. We want to understand if it gives you a binary, how close is that binary? Because the closer you're leaving the binary, the quicker it merges and can form a type 1a supernova. So the type 1a rates are absolutely dictated by how these interactions proceed. Now, the closer, the more supernovae. Now, supernova rates are measured in the universe, so this is a wonderful observable to use as a validation for the codes. So that's how the simulations interact with our understanding of type 1a's.
Okay. Thank you, and let's thank Orsola for her talk. And I'm just going to put this here. I also want to present Orsola with a gift from the General Chair of the SC19 conference, so Michaela Topher, to say thank you very much. We were inspired about the stellar collisions.
Is it chocolate?
Yes.